All right, welcome to the Math Professors, and today I'm going to cover hyperbolic functions, and to do that we're going to start out with what we know about trig functions. So looking at the unit circle, we know that solutions of the unit circle are points cosine of t, comma sine of t, where t is the angle. And that really means that the cosine and the sine are parametric solutions of that unit circle, x squared plus y squared equals 1, or plug it in x and plug it in y, the coordinates of the solution points. We get the Pythagorean theorem cosine squared of t plus sine squared of t is equal to 1. Now the hyperbolics are similar in nature. So instead of using the unit circle x squared plus y squared equals 1, we're using the hyperbola x squared minus y squared is equal to 1. So really what we know is the hyperbolics are the parametric solutions because of angle t, because it's going to be the intersection through that angle t to that hyperbola. So looking at the x squared minus y squared is equal to 1, plugging in the cosine of t, the hyperbolic cosine of t and the hyperbolic sine of t, we get an identity for the hyperbolics. So I'm going to define these in terms of E, so let me pause it and be right back, and I'll write all the information. So I'm going to go through the derivation of how to find the hyperbolics in terms of e to the x. So we know a function can be written as its even part plus its odd part, where the even part of the function is going to be equal to f of x plus f of negative x, all divided by 2. And then the odd part of the function is going to be f of x minus f of negative x divided by 2. So we can add these things together, and what we'll see is that these f of negative x over 2 and negative f of negative x over 2 are going to cancel. And then you're going to have f of x over 2 plus f of x over 2, which is going to give us f of x. Now, if I give just a basic like a polynomial that would be more familiar with, if I have something like 3x to the fourth minus x cubed plus 5x squared plus 1, it can be shown by using these things that the even part is going to be, kind of what you'd expect. The even part of the function is going to be 3x squared plus 5x, and the odd part of the function is going to be negative x cubed plus 1. And then the addition of these things are going to be this. And these things will hold the property of, well, we know what happens for an even function. So a function is even this happens if f of negative x is equal to f of positive x. And an odd function has this property. It says that f of negative x is going to be equal to negative f of x. So and we can kind of prove that here. If I plug in negative x, I'll mess this up a little bit. This should have been x squared. Boop. And then plus 1. There we go. So this should have been x squared. There we go. So we can prove this if I plug the negative x into the even part of this. We see that even powers is going to turn the negative x into a positive x, so this will be true. And then for the odd parts as well, I messed this up kind of quite a bit. Quite a bit is going to be this. Okay, so really what it comes down to is the hyperbolic cosine and the hyperbolic sine functions are actually the even and odd parts of e to the x. So I'm going to write that up here. So here are the hyperbolics in terms of the e form. So the hyperbolic cosine of x is e to the x plus e to the negative x over 2, and the hyperbolic sine is going to be e to the x minus e to the negative x over 2. And we can see this as, for e to the x, this would be f of x, this would be f of negative x all over 2. So we can say that this is the even part of e to the x, and this is the odd part of e to the x. What's interesting about this is we know some, here's like a known formula, or a known identity. Let's say formula. Let's say identity, because that's really what it is. A known identity. So what I know is that 2 sine of x cosine of x is equal to the sine of 2x. And that's something that we've taught in like a basic pre-calculus or trigonometry class. So what I want to do is I'm going to show that this one actually works for the hyperbolics as well. So let's check. Let's check this. What about 2 the hyperbolic sine of x times the hyperbolic cosine of x? Well, the hyperbolic sine of x is this, so this is going to be 2 times e to the x minus e to the negative x all over 2, and then the hyperbolic cosine is just a plus instead, so e to the x plus e to the negative x all over 2. So we can see that these 2's will cancel, and then I can multiply these numerators together, so e to the x times e to the x is going to be e to the 2x. Outside is going to be e to the x times e to the negative x. Well, this is e to the x over e to the x, which is going to be 1. Inside is still going to be the opposite of that, so e to the x, e to the negative x. So this is going to be 1, this will be negative 1, so those things are going to cancel. Plus, we're going to have, when I multiply these things, this is going to be e to the negative 2x, and this is all going to be over 2. Because those 2's cancel, that will cancel. So what I have is I have e to the 2x plus e to the negative 2x all over 2. And what we can see is that is this function, except instead of x's, we have 2x. So this is actually the hyperbolic sine of 2x. Now there are names for these things that you'll hear is the hyperbolic cosine is considered the cosh of x, and the hyperbolic sine is the sinh, kind of rhyming with pinch, so sinh of x. But I'll likely just call them the hyperbolic cosine and hyperbolic sine. All right, so I want to look at the graphs of these things and eventually their derivatives and their integrals. So here are the look at the graphs of the hyperbolic sine, the hyperbolic cosine, and the hyperbolic tangent. Now we can see that the hyperbolic sine is actually bounded to e to the more likely actually asymptotic to e to the x over 2 and then e to the next negative x over 2. And similarly, the hyperbolic cosine is asymptotic to e to the negative x over 2 and e to the x over 2. Or should be minus 1 because that's flipped. So, what we're going to have is also the hyperbolic tangent is going to be asymptotic or bounded by y equals 1 or y equals negative 1. So really what I wanted to show you is the hyperbolic tangent, y is equal to the hyperbolic tangent, is defined kind of as you would expect as the hyperbolic sine over the hyperbolic cosine. So if we want to look at the hyperbolic tangent of x, this is going to be equal to the hyperbolic sine of x divided by the hyperbolic cosine of x. And we can find the formula in terms of e to the x as well. So this is e to the x minus e to the negative x over 2. And the hyperbolic cosine is going to be e to the x plus e to the negative x over 2. And then those 2's will cancel. So this will finally be equal to e to the x minus e to the negative x over 2. I'm sorry, not over 2, but e to the x plus e to the negative x. So it'll simplify to that. So finally, their derivatives and then their integrals. The hyperbolic sine of x. So we know that this is going to be equal to e to the x minus e to the negative x all divided by 2. And I can pull out that 1/2, so this is equal to 1/2 times e to the x minus e to the negative x. And a lot of times when you're taking derivatives, it's easier to pull out that constant. So then if I want dy dx, this is going to be equal to 1/2 times the derivative with respect to x of e to the x minus e to the negative x. So this is going to be equal to 1/2. The derivative of e to the x is itself, and the derivative of e to the negative x would be negative e to the x. So this would be minus e to the negative x. So we're going to get 1/2. This would be e to the x plus e to the negative x. And we can see that this will simplify to e to the x plus e to the negative x all over 2. So kind of what you would expect is the derivative of the hyperbolic sine is the hyperbolic cosine. Now what is interesting about the hyperbolic cosine, its derivative, so let's let now y equal the hyperbolic cosine of x, which is e to the x plus e to the negative x all over 2. If I want to find the derivative, so say the derivative with respect to x of the hyperbolic cosine of x, this is going to be, again, 1/2 times the derivative of e to the x plus e to the negative x. And the derivative of this is of e to the x is e to the x. The derivative of e to the negative x is minus e to the x. So this is going to be 1/2 times e to the x minus e to the negative x, which we can see is just a hyperbolic sine, because this is all over 2. So this is equal to the hyperbolic sine. Now this throws students for loops, because we know the derivative of the sine, the regular, the trig sine function is going to be the cosine function, and then we know the derivative of the cosine function is the opposite of the sine function. But with hyperbolics, we don't see this opposite behavior, that the derivative of the hyperbolic sine is the hyperbolic cosine, and then also the derivative of the hyperbolic cosine is the hyperbolic sine. Now this will allow us to find the derivatives of all the hyperbolic functions. We have tangent and secant and cosecant and so on, because we have their reciprocals and their ratios. So we'll find the derivative of the hyperbolic sine, and we'll introduce basically a new trig function, or hyperbolic function. I want to find the derivative with respect to x of the hyperbolic tangent of x. So I know that this is the derivative with respect to x of the hyperbolic sine of x over the hyperbolic cosine of x. And I'm just going to use what I know about the derivatives of those two parts. So this is going to be, using the quotient rule, the derivative of the top times the bottom minus the top times the derivative of the bottom, all over that denominator squared. And then simplifying this, I know that the top is your, well, it's a Pythagorean theorem when it comes to hyperbolas, but we know that this is of the form the hyperbolic cosine squared of x minus the hyperbolic sine squared of x, which we know is 1. So this is going to be equal to 1 over the hyperbolic cosine squared of x. So this is defined to be the hyperbolic secant squared of x. So this is the hyperbolic secant of x, but being squared. Now we can actually show the derivatives of all the trig functions. We can derive them all, but let me write a list over here, and then we can kind of just keep track of them. So what we know is the derivative with respect to x of the hyperbolic sine of x is equal to the hyperbolic cosine of x. The derivative with respect to x of the hyperbolic cosine of x is equal to the hyperbolic sine of x. The derivative with respect to x of the hyperbolic tangent of x is going to be the hyperbolic secant squared of x. And then similarly, we can do the derivative with respect to x of the hyperbolic cosecant of x, which we know if this was trig functions, the derivative of the cosecant of x is negative cosecant of x cotangent of x, but there won't be any negative sign change here. This is going to be the cosecant, hyperbolic cosecant of x times the hyperbolic cotangent of x, and the derivative with respect to x of the hyperbolic secant of x is going to be the hyperbolic secant of x times the hyperbolic tangent of x, and then finally the derivative with respect to x of the hyperbolic cotangent of x is equal to the hyperbolic cosecant squared of x, which also means their integrals or their antiderivatives would go the other way. So let's practice just a couple derivatives, and then I'll just do a couple integrals, and that'll finish this video. Let's do them over here. Let's apply some of these. So, example. Let's say find the derivative. So, A. What if I have y, which is equal to the natural log of the hyperbolic That h is right next to there. The hyperbolic cosine of x. So we know when we're taking the derivatives, we have to work outside in. So the derivative of y with respect to x is going to be the derivative of the natural log expression first, which is going to be 1 over what's inside, multiplied by the derivative of what's inside. So this is f prime of g of x multiplied by g prime of x, where g of x is the inside. So this is going to be the hyperbolic sine of x, which you can see is going to be the hyperbolic sine over the hyperbolic cosine. So this is going to be the hyperbolic tangent of x. B, if I want to find something like y is equal to x cubed hyperbolic tangent of x, well, we can use a product rule. So dy dx is going to be the derivative of the first times the second plus the first times the derivative of the second. We know the derivative of the hyperbolic tangent is going to be the hyperbolic secant. So hyperbolic secant squared of x. Now, similarly, we can find their antiderivatives as well. So let's do a couple antiderivatives just with these rules over here for help. So let's see, evaluate the integral. So A, so let's go to this example. Let's find the indefinite integral of the hyperbolic sine of x over 3 dx. Now it'll be very similar to if I was asking for the integral of just the sine of x over 3. That we know that the antiderivative of the hyperbolic sine is going to be the hyperbolic cosine, but then I'm going to have to divide by that coefficient of 1/3. So this is going to be the hyperbolic cosine of the inside piece, all divided by its coefficient. Really, this is nothing more than a u substitution. Let u be this. Plus c, so this is going to be equal to 3 hyperbolic cosine of x over 3 plus c. And b, what about the integral? And I'll actually introduce a u substitution. So what about the hyperbolic cotangent of x? So if I want to do this, this is going to be the integral of the hyperbolic cosine of x over the hyperbolic sine of x dx. So then u is going to be your hyperbolic sine of x, and du is going to be the derivative of this, or the differential of this, which is going to be the hyperbolic cosine of x dx. So this thing ends up being really just the integral of 1 over u du. So this is the integral of 1 over u du, which is the natural log of the absolute value of u plus c, where u is going to be equal to that sine, hyperbolic sine. So this is the natural log of the hyperbolic sine of x plus c. Now sometimes they ask for a definite integral, and for the heck of it, we'll do just one of them. So let me pause it. I'll erase it all, and then we'll do one big kind of. Your sine function is your u and your dv. So I'm just going to say u is equal to e to the theta. So then dv is going to be the hyperbolic sine of theta d theta. So that means du is going to be equal to e to the theta d theta, and then v is going to be its antiderivative, which is going to be the hyperbolic cosine of theta. So using uv minus the integral of v du, this is going to be uv, so e to the theta hyperbolic cosine of theta minus the integral of v du, which is going to be the hyperbolic cosine of theta times this. So I'm going to actually put this e in front. So hyperbolic cosine of theta times e to the theta d theta. So this is going to be. And then we'll notice in this particular spot, I'm like, hey, wait a second. It did not get simpler. But as you can tell, if you've done any repeated integrals before that, we do it again, and we're going to get a form of the original. So let's do it again. U is equal to e to the theta. Dv is going to be equal to the hyperbolic cosine of theta d theta. du is going to be equal to e to the theta d theta. So then v is going to be its antiderivative. So this is going to be the sine h of theta. So this is going to be equal to e to the theta hyperbolic cosine minus, what I get here, so uv. So e to the theta hyperbolic sine of theta minus the integral of v du, which is going to be e to the theta hyperbolic sine of theta d theta. Now I can get rid of the parentheses by distributing the negative, so that's going to distribute here, and then the negative is going to turn this into a positive. And really what we have here is I have, pulling out that 2, this is 2 times the antiderivative of e to the theta hyperbolic sine of theta d theta. So what I can see is I get another expression, e to the theta hyperbolic sine of theta. So if I subtract it on both sides, minus 1 here, 2 minus 1 is just going to be equal to the integral of e to the theta hyperbolic sine of theta d theta is going to be equal to just this expression. So e to the theta hyperbolic cosine of theta minus e to the theta hyperbolic sine of theta. Now I really wasn't asking for just, this expression. I did want double this expression. So in order to turn this back into 2, I can just multiply both sides of this equation by 2. So I can just multiply this by 2. Now, if I want to find the antiderivative of this from 0 to the natural log of 2, I can just evaluate this from 0 to the natural log of 2. Now, the reason why I put a definite integral in here is because in order to evaluate the trig functions, we have to turn them back into their exponentials. So I'm going to have to evaluate the hyperbolic cosine at natural log of 2 and also the hyperbolic sine at that as well, at natural log of 2 and also at 0. So let's kind of just do it to the left over here just for some work. So if I want the hyperbolic cosine, well, the hyperbolic cosine of the natural log of 2 is going to be equal to e to the natural log of 2, I guess I don't need parentheses, plus e to the minus natural log of 2 all over 2. Now I have to be careful that this will become the natural log of 2 because really e and the natural log are touching. They're inverses and right next to each other, so it's e of that. But this is not e of the natural log. This is e of, minus the natural log. So when we do that, this is going to be e to the natural log of 2 plus e to the natural log of, well, this negative 1 is going to go in the power, so it's going to be a half all over 2. So e to the natural log of 2 is 2 plus e to the natural log of a half is going to be a half all over 2. So common denominators, this is going to be 4 over 2 plus 1 over 2 divided by 2, multiplying both those by 2. So I'm going to have 4 over 4 plus 1 over 4, which is going to be equal to 5 over 4. Now, without doing all the work, I know the hyperbolic sine of the natural log of 2 is this exactly the same expression, except there's a minus sign. So instead of this being plus, this is going to be minus. So this is going to be 4 over 4 minus 1 over 4, which is 3 over 4. And if I want to find them at 0, the hyperbolic cosine of 0 is going to be, e to the 0 plus e to the minus 0 all over 2. So this is 1 plus 1 over 2. So this will be equal to 1. And then the hyperbolic sine of 0, and we graphed this as well just a little bit ago. We can tell that went through the origin. And the reason why this is e to the 0 minus e to the negative 0, which is still e to the 0 all over 2. So 1 minus 1 over 2, which is going to be equal to 0. Okay, so finishing this off, this is going to be equal to a value at the top, 2 e to the natural log of 2 hyperbolic cosine natural log of 2 minus 2e to the natural log of 2 hyperbolic sine of the natural log of 2, and then minus when I plug in 0, 2e to the 0 hyperbolic cosine of 0 minus 2e to the 0 hyperbolic sine of 0, and I know their evaluations. Natural log of 2, this is going to be 5 over 4. Natural log of e to the 2 is going to be 2, so this is 4 times 5 over 4 minus 2 times 2, which is going to be 4 times 3 over 4 minus e to the 0 is going to be 1, so this is going to be 2. The hyperbolic cosine of 0 is going to be 1 minus the hyperbolic sine of 0, which is going to be 0, so 2 times 0. So that's gone. So this is going to be 5 minus 3 That's interesting. 5 minus 3 minus 2, so this would be equal to 0. And that's all I have. So until the next one. Oh, please try to subscribe. Thank you.